our definition of a theoretical probability was to count out the number of ways what we wanted could happen and divide by the total number of ways something could happen. So for our event A, the probability of A is the number of ways A can happen divided by the number of ways in the sample space, S. Which really means what we're doing is counting sets. So I'm going to need to steal back to the first time we did any work in sets and think about how we visualize and draw and understand and look at sets. For those of you who have seen them, the idea of a Venn diagram comes into play here a little bit. But I'm going to start with the idea of I have a sample space, some giant pile of outcomes. Please notice the word elementary here. These are single events, simple items. And then I have my thing A, and that's some collection within my set S. If we're talking about pick a card, and my success is I drew a queen, well, then there should be how many items in A? My 4 queens, hearts, spades, diamonds, clubs, and all of the other 48 cards will be out here. But that means that a total of all 52 events show up in S. So A is some sub-collection, some subset of S. Then I'm going to write A prime. Sometimes it's written A with a little C up there. Sometimes it's written A with a bar over it. But I believe our textbook only uses this A prime. Is the complement of S. And it's all the rest of it. It's everything outside of A. So our subspaces are divided into 2 pieces, the stuff inside A and the stuff outside A. A prime is that section, the complement. Let's change our item A. Jason, pick a suit. Okay, so now I'm going to call success. I picked spade. That's the rest of it, right? This is the complement. But if I tell you to pick a card, you have to get one from either the pile on the left or the pile on the right, right? That's the only 2 choices here. You're either in that one or in this one. We had a rule on Friday that said the chance of something happening has to be yes, but we even were more specific about it. It's okay. Really what it's come down to is these are my only 2 choices. If I tell you to pick a card, you either get a card from the pile in my left hand or a card from the pile in my right hand. If those are the only 2 options, then those cover everything, don't they? What's the chance that when you pick a card, it comes from one of these two piles? 100%. It's a guarantee. The total of all of my probabilities for the options available has to be 100%. That's 1. How many spades in the deck? So what's the chance of a non-spade? The chance of something I want happening and its complement must add up to 100%. So the chance of the thing I don't want is 1 minus the chance of the thing I do want. So if the chance of drawing a spade is 13 out of 52, then what's the chance of drawing a not spade? Subtract from 1. By the way, you are more than welcome to simplify these. 13 out of 52 is 1/4. So this becomes 3/4. I'm going to surprise no one. This is called the rule of complements. Questions? In the same vein, you draw a card. Chance it is not a queen. One minus the 4 out of 52 chance to get a queen. 48 out of 52. It's easier to me to count the ways the queens happen because there are fewer of them. Questions? I used a very particular word when I was thinking about my two piles that made up the spades and the non-spades. I said, you pile from the cards in my left hand. You get a card from the pile in my right hand. What was the word I used between those two? You pick a card. It comes from this pile. It comes from this pile. There's a word that goes there. In conjunction. Take you back to your English class. Or. It's either in here or it's in here. Okay. From a mathematical perspective, or similarly, and need to be used very carefully. I'm going to use the word or with the word union. I'm going to use the word and the word intersection. And they represent having more than one event. Wait a minute. In my picture, an event was a subset of my outcomes. So I have my sample space here, and I have an outcome. This time I have more than one. So I have two outcomes, outcome A, outcome B. I would like you to shade, mark, or somehow delineate in that picture what's covered when I say A or B. Yeah, what's covered when I say A or B? What parts of this picture are covered? Aha. Right? The whole thing. However, over here, when I say and, because this is what you said, like you said the A part and the B part. But it's really not. Over there, it's the A part or the B part. In this side, I want to do the A part and the B part. You need to be in A and in B at the same time. Just this middle section here. The intersection of my two sets is their overlap. The union of my two sets is the combined pieces along with the overlap. Page 160 has these diagrams as well. So, earlier, we figured out the chance of getting a queen when we did the chance of not getting a queen. We figured out the chance of getting a spade when we did the chance of not getting a spade. So now I want to know, you pick a card. What is the chance it is a queen or a spade? Now, I'm using or, so I'm thinking of this picture, and I'm counting within this picture. How many queens are there? And how many spades? So there's 4 things in the circle marked A. There's 13 things in the circle marked B. 13 and 4 is 17. There should be 17. Why are you shaking your head, Jason? Bing, 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 bing. There's something in our intersection that I counted twice. And since I counted it twice, I have to pull it out once, right? So I only count it once. I either count it with the A's or with the B's. So if I count it with the A's and I count it with the B's, then I have to pull it out for every time it shows up here. So what I'm going to write is I'm going to write that this is the chance of a queen plus the chance of a spade, but that double counts, right? So I pull out the chance of queen and spade. Now, there only happens to be one of those, and that's fine, but I'm doing this as probabilities. So I'm going to write these as out of 52s. In our case, 4 out of 52 plus 13 out of 52 minus 1 out of 52. I keep saying the number 1 as I'm writing. I start to write the 1. Sorry about that. Which means I get 16 out of 52 instead. Which you could, again, simplify the fraction if you want, 4 out of 13, or you could grab your calculator and give me a decimal. I'm perfectly happy with that. If you're going to give me decimals, I'd prefer at least 2 or 3 decimal places, but I'm a geek, I like fractions. This idea, in general, is called the inclusion-exclusion principle. I included something too many times, so I have to make sure to exclude it as well. The chance of A or B is the chance of A plus the chance of B minus the chance of both. So really, in order to do an or, I have to do an and. questions? Yes, sir.
Like in between the A and the B right there, that U symbol, that's the or.
That's our union.
That's the
intersection. I always remember it as the U for union and the N intersection. But yes, it's or and and. And again, I find that N is that N right there, and then I can remember the other ones the other way. Whenever I talk about an and, I'm really looking at two things happening at the same time. That's also called a joint probability. I'm joining two things together. There is a logic term that uses that and symbol as well called a join. So this is where that comes from. Joint probabilities must be smaller than either of the non-joint probabilities, which is less likely to happen. You pick a card and it's a queen. You pick a card and it's a red queen. The second one is more unlikely to happen because there are fewer options, right? If I can think of red and queen, has to be smaller than the chance of queen. It also has to be smaller than the chance of red, right? But that's what a joint probability gets us. But I didn't do any subtracting. When I was thinking earlier about my spades pile, my not spades pile, why didn't I have to do any subtracting? This is not a crazy question. I promise you there's a real obvious answer right in front of you about my hands. And there's nothing that is in my left hand and my right hand at the same time, yes? That means this part is 0. There's no overlap between my two sets. If A and B are separated sets, there's a name for that. If A intersect B is empty, we say A and B are disjoint sets. No join, okay? And in terms of events, they represent mutually exclusive events. Events that cannot happen at the same time. You cannot be a spade and not a spade in a single card. You cannot have a 5 show on your die and have a 3 show on your die at the same time when you only roll 1. You can't have the coin come up heads and tails together. Those are exclusive, mutually exclusive events. They can't happen together. And that means that this number is 0. And in order to do an OR, I just have to add the 2. There's nothing to subtract. I'm going to use the phrase mutually exclusive fairly frequently. And there's another phrase that goes with it. But this can apply to many events. You look like you're unhappy with that. Talk to me.
What is, are you trying to say C, or are you trying to do a union split that after the equal?
That's a 0.
zero, okay.
The probability of A intersect B is a 0. That's a number. The number 0. Whew. Yes, my handwriting sucks. Call me on it. If I have a collection of events and they cover every possible outcome, that's called collectively exhausting events. Now, these A's may or may not be disjoint. If they are disjoint, then I'm going to use both phrases, collectively exhausting and mutually exclusive. But collectively exhausting is its own separate category. I really like collectively exhausting and mutually exclusive. There's no overlap between them. I can just count each pile. But there might be cases where we do have overlap. Binary events, heads, tails. As we were saying earlier, queen, not queen, spade, not spade, heart, not heart. Those are mutually exclusive. They're also collectively exhausting. Because if you pick a card, it's either a queen or not a queen. But I can also think of hearts, spades, clubs, diamonds as collectively exhausting. If you pick a card, it's got to be from one of those 4 sets. If you're dealing with a standard deck of cards. If you're dealing with a different deck of cards here, you could get the Jack of Eagles. That's a very different deck. It's also a really good sci-fi book by James Blish. Questions?
What is the S stand for?
Our sample space, the whole thing. That's our box on the outside. More questions?
Why is it on the outside? Yes.
That is the representation of our whole sample space. That's all possible things that could happen. And what I'm saying here is that these events are collectively exhausting if they cover every option. So you can literally think of it as I cover all of the square with those circles, A1 through AN. Does that help with the image? Okay. You're welcome. Sometimes we have extra information when we're figuring something out. I just rolled this die. What is the chance I got a 2? One out of 6. But now I'm going to cheat. What is the chance I got a 2 if you know the number I got is even? Wait a minute. That if changes your sample space. It changes the things you're looking out of, right? How many numbers that I can roll here are even? And if the chance I got a 2, it's either a 2, a 4, or a 6 if I tell you it's even. So the chance is now Instead of 1 out of 6, it's 1 out of 3. Formulaically, we're going to write this like this, and we're going to say the probability of a given B. This extra piece, I told you the number I rolled was already even. That's the additional given information. Does having more information change our result? In this case, the answer was yes. Formulaically, how do we picture this? Here's my sample space. I have some event B. And now I'm asking, what's the chance that I have A? If I tell you we have B, that means you already know you're in here, right? That means that A should overlap this. And what I'm really looking at is just the part of A within B. So I can think of myself as covering up all the rest of this and just looking at this piece versus this circle. Wait a minute. What's the name for this piece here in the middle? A is that whole circle on the left. So just the middle piece, that lens shape. That's our and, our intersection. So really, I'm just looking at the chance of being in there as a piece of being in here. What's the chance I'm in the and part when I tell you I'm in that B part already? Now, this looks like it's a little more complicated of a formula, but let's put this back in terms of the dice we were just talking about. The chance of 2 given even. I feel like you said earlier, the chance of getting a 2 is 1 out of 6. But Jason, you said, how many even numbers are there? But that's out of 6. So the chance of getting even is 3 out of 6. And then I simplify my fraction. You pick a card. What is the chance that my card is a heart? 13 out of 52. But what is the chance it's a heart if I tell you it's red? I'm going to follow this formula right here. In order to answer this, I need to know what's the chance of being a heart and being red. And then I'm just going to divide that by the chance of being red. Now, fortunately for me, in a standard deck of cards, all the hearts are red. So all 13 of those hearts are also red. So that upper number is still 13 out of 52. But how many red cards are in the deck? Because I have all the hearts and I have all the diamonds. And when I simplify that fraction, what do I get? This is why I like fractions, because, oh, they're both over 52, so I can cross that out. That's 13 out of 26. 13 out of 26 is exactly a half. Now, these do not have to be particular items related to any dice or cards or anything else. Page 163. Of the population of age 16 to 21 people not in college, 13.5% are unemployed, 29.05% are high school dropouts, and 5.3% are unemployed high school dropouts. Wait a minute. I've been given 3 descriptors, right? How many sets do I have to work with here? I really only have 2. Unemployed and dropouts. Because this group is unemployed and dropouts. That's the intersection of our 2 sets. So now if I ask, what's the chance someone's unemployed if I tell you they're a high school dropout? That's a conditional probability. The chance of unemployed given that they are a high school dropout. So that's P of U given D, using the letters they've used here. So I take the and, which is why I needed that part, and divide by the D. Probability of being a dropout, 29 is the bottom, 5.3 is the top. I get 18%. So that means if you know in advance, hey, this person is a high school dropout, there's an 18% chance based on this survey that person is unemployed. I can also use this to rearrange. Because I have this formulaically up here, I can actually rearrange and write that the probability of A and B is the probability of A given B times the probability of B. That is an important distinction. Because here's something that goes counter to what you were telling me on Friday, Felix. It's in the very same vein, but you said something about multiplying, right? Here's my multiplying. But that first one requires me to think about condition. Most of the time. This means that if I knew a conditional probability of somebody being unemployed given they were a dropout, then I could work out the and instead directly. It all depends on what I'm given versus what I actually have as information. There's another example at the bottom of page 163 about people watching video on demand versus watching things on television. There is also, unfortunately, a frequently used different method of writing out a probability. This makes me nuts and I don't like it, but it's in the book and it's in real life, so I want y'all to see it. And that's the idea of odds. If I say the odds are 1 to 2, that means there's twice a chance of it not happening as there is happening. So the odds in favor of something, 1 to 2. What is the probability that the thing I want is going to happen? It's not 1/2. It's 1 for every 2 nots. So it's really 1 out of 3. It's A over A plus B, not just A over B. By the way, if I say the odds against something, I reverse the 2 ideas. If the odds in favor are 1 to 2, then the odds against are 2 to 1. And again, the same thing goes for the probability conversion. That's still 2 out of 3, not 2 out of 1. That doesn't make sense. I can't have a probability bigger than 1. And 2 is definitely bigger than 1. Why do I give this? Well, because a lot of odds are given today countrywide in sports betting, which is legal now. So unless you're in the NCAA, don't do it. You'll get thrown out of your sport. But that's where this shows up a lot. So I wanted you to see this notation here at the top of page 164. I will use it very infrequently, but a couple of our questions do address this. Please make sure you convert back to regular probability. Let me go back. My dice. I'm going to roll this white die. Then I'm going to roll this red die. Does the outcome on the red die have any effect on the outcome on the white die? What about the other way around? The outcome on the white die have any effect on the outcome on the red die? I'm going to flip coin, and then I'm going to roll the die. Will the coin affect the die? Vice versa? Okay. If knowing any information does not change our probability, the opposite of conditional, then my two events don't have any influence on each other. We're going to call those independent events. This is not cause and effect. This is just to say the probability is unaffected. It's just a probability. And the other way around, if those two are not equal, then we call the events dependent. Determining what is independent and what is dependent is as simply, in this case, just the study of the probabilities. So let me think about this. We really should be counting out our sample space. I should be writing it all out. I'm going to pick a small sample space. I'm going to flip two coins. I would like to compare what is the chance I get a heads on the first coin? And what is the chance I get a heads on the first coin, given I got a tails on the second coin? I brought two. But what is my sample space? What are all the possible things that could happen when I flip these two coins?
Heads or tails, and then really weird, not really, if it's possible, but it's not probable, sideways.
Nope, just heads or tails. We're going to go with the real ones. It's either going to add heads or tails. But that's true for each coin, right? So how many possible results are available in the whole scheme of things, looking at the results from both coins together? Right. My sample space looks like this, where we're putting the coins in order. First coin, comma, second coin. So, based on that sentence, what is the chance I get a heads on the first coin? Well, let's look at this. How many of these outcomes have heads on the first coin? Out of 4, right? So the chance of this happening is 2 out of 4, or half. But now my conditional probability. The formula for my conditional probability is the probability of the and over the probability of the second. How many of my outcomes have a head on the first and a tail on the second? There should be a show of hands here. Just one. Out of the 4. But how many of them have a tail on the second? Aha. HT and TT. But that simplifies to be the same thing, right? So these events are independent of one another. Having the additional knowledge did not gain me any change in my chances. I like independent events because when my events are independent, I can just multiply directly. Notice that changes my formula. There's no longer a conditional probability in there. It was P of A given B times P of B. But now P of A given B and P of A are the same. This is particularly useful to me in things like reliability. So, how many of you have had your laptop crash and die on you? Was it recoverable? Oh, good. I lost a hard drive once. It died a horrible flaming death. Turned out to literally, physically cause a head crash, and I lost that entire sector as the head was scraped. But I had backups. You have a bunch of stuff in the cloud, yes? That's on someone else's computer. Usually a computer over in a data center on a big rack, giant hard drive being stored with a bunch of people having access to it. What happens if that hard drive crashes?
They usually have a tape backup in another, well, maybe not anymore, but they used to have tape backups in another location.
I want you to understand, physical hard backups meant that every day or every so often, I would go into the computer lab and I would mount a reel of tape the size of your chest on a rack, push record, and record the hard drive. That usually took 6 hours per drive, per center. We ran those 24/7. Nowadays, in order to cheat that, your stuff is not on one computer. Whatever you've got in the cloud is on more than one computer. Why? To waste disk space. There's got to be a reason here.
one of the computers is destroyed, you don't want to lose everything.
And that's my backup, right? The other computer. So let's suppose that my computers are independent of one another. And what happens on one won't affect the other. A computer that has a 99% uptime is still down 1% of the time. If your stuff is on two computers that are independent of each other, what's the chance it's down and unavailable to you? Now, in this case, the it that is down is my data. What's the chance I can't get to my data? I hope it's a lot less than that. How did you get 0.5%?
It's divided 1%.
I have no idea why that would be the right thing to do.
Yeah, the one computer, and that's the second computer, so computers,
Mhm.
it's 1%. Then I can multiply it with 1%.
Because the event of going down is independent on computer A and computer B, I'm going to use this idea right here. The chance that both computers are down and I can't get to my data is the chance of the first one being down times the chance of the second one being down. (1% squared is 0.0001. Right? 1, 2, 3, 4, yes. Which is a much smaller number. Instead of 1 in 100, it's now 1 in 10,000. If it's 3 computers, then one in a million. Problem is that there are billions of computers out there. So realistically, I probably need to be on more than 3 computers. Most data servers back up to 5 or more different sources. Redundant services are there specifically to keep this idea together. When we talk about something that is 6 nines, if I subtract this from 1, I get 9, 9, 9, 9, 9, 9, 6 nines of reliability. There is a very nice way to read contingencies, ands, and ors based on our way of writing the events that go on. I would love to show you such a joint probability table, but I have less than a minute left. So when we come back, we will have a discussion of contingency tables. But that's not Wednesday, because Wednesday is the test. Wednesday anyway? And on Friday, we don't have class because I will be on the other side of Pittsburgh at Moon Township at a career fair for the actual assignment. That means after Wednesday, my next chance to you is Monday. So Take your time, look through these items, study for the exam. I will post the key to chapter 4 and the key to the review sheet within the next 10 minutes. I will see you all on Wednesday.